In angular measurements, the vernier bevel protractor is followed by another important instrument, sine bar. Here we are discussing about the principle of sine bar. In principle of sine bar, we are considering simple trigonometry. Consider a right angle triangle. So this side is the hypotenuse. This, if the angle is this one, given angle is this one, and the opposite side is this side is our opposite, and this is our adjacent side. And in sine bar setup, we can relate all these hypotenuse and sides with the sine bar setup. So the sine bar surface forms the hypotenuse. Then the stack of gauge blocks is our opposite side, and the adjacent side forms the surface of the surface plate. So this one is the surface plate. So this surface forms the adjacent side. And if the angle to be known is theta, that is the angle to be checked is theta, then we know that this theta, the sine, we can relate these relations. So the sine bar, it is having a length like this, length between the rollers. So that is L, that is standard, that is a known length. And this stack of gauge blocks is also known, and that is H. So if L and H are known, we can have a relation that is sine theta is equal to H by L. So from this equation, we can find the value of theta sine inverse of H by L. So this is the principle and the relationship used to determine the unknown angle using a sine bar. The parts of the sine bar, it has got an upper surface like this. So this is the upper surface where we are actually fixing our workpiece over here. Then it has two end faces. Then two precision rollers are there. These rollers are actually fixed to the sine bar, firmly fixed using screws. Then some relief holes are also provided. So the function of these relief holes is that one is that to reduce the weight of the sine bar, and another thing is that using the clamping bolt. So sometimes we have to clamp the sine bar with the angle plates. So for that purpose, we can insert bolts through these holes. Then lower surface is there. Then important dimension of a sine bar is its length. So the length is measured between the center of these two precision rollers, and the length availability is between the common lengths available are 100 mm, 200 mm, or 300 mm. And sine bars are made up of high carbon, high chromium, corrosion resistant steel, which can be hardened, ground, and stabilized. Here we are discussing about use of sine bars. So sine bar has got three important uses. Specifically two important uses. One is location of a workpiece at an angle below the machine spindle. Then another is that checking or measuring the unknown angle. This is the two important things. So first we will consider the locating any work to a given angle. So the setup is given. So this is the sine bar, and we can fix a workpiece like this. Okay, so it's a block. If the block is like this, if we wanted to drill a hole in this axis, okay, so this hole is like this, and this is at an angle theta to the vertical of this vertical axis of this workpiece. And here also that theta is equal to this theta. So that theta angle we have to tilt the sine bar. So the theta is given us using the equation that sine of theta is equal to H by L. So L is fixed because L is a standard provided by the sine bar. So we have the variable is that h. So from this equation, theta is known and L is known. So from this equation, we have to find what is the h, that is the opposite side. And after finding the h, then we have to make that h precisely using gauge blocks. So if we are precisely stack or run the gauge blocks to obtain the required height h, then we can have the accurate setup with the angle theta. A second use of sine bar is checking or measuring unknown angles. This is further classified into unknown angles of smaller workpieces and the unknown angles of larger workpieces. So first we will consider the unknown angles of smaller workpieces like this one. So workpiece is less than the size of the sine bar. So it can be placed easily over the sine bar surface like this. So in this setup we are using different equipments. One is sine bar. Okay, so this is the sine bar is the first equipment. Second one is surface plate. Third one is gauge blocks. And in addition to that, we are using dial indicators. So this is the fourth equipment. So four equipments are used in measuring the unknown angles using a sine bar. Sine bar alone cannot measure the unknown angles. So this is a setup. More detailed view of the setup is shown in this picture. So here, after setting the workpiece over the sine bar, we are clamping, we are arresting the unwanted motions like this. Then after setting, we can't set it directly because we don't know this angle. What is the angle theta? We don't know angle theta. So in order to find that angle theta, the condition is that we have to make this surface, the top surface of the workpiece, truly parallel. So that parallelism is checked using a dial indicator. So after setup, approximate setup we are done initially. So using trial and error, we have to make it exact parallel. So if it is exactly parallel, the deflection will be 0 for this dial indicator for the position 1 and position 2. So it is sliding from position 1 to position 2. So throughout this movement of the dial indicator, the deflection should be the change in deflection should be 0. Otherwise, it will show the same deflection. If the deflection has got a variation, we have to measure that variation, whether it is placed downwards or placed in an upward direction. So that has to be measured using the dial deflections. So that distance that we can tell that is dx. So that distance has to be adjusted with the changing the stack of the slip gauges. Okay, changing the stack of the slip gauges. So this dx has to be compensated by the change in dimension of the slip gauges. So using trial and error principle, at last we have to finally reach that the deflection is 0, that is the changing deflection is 0. Once it is achieved, we can tell that the top surface is parallel. Now that is our condition. Then we have to note down the h. What is the slip gauge height? That is the final height. So that height has to be taken. Then using the equation sine theta is equal to h by L, we can find value of unknown angle theta. Now h is known and L is the standard, that is the length of the sine bar. This picture shows the measuring of angles for larger size components. That is our second method of measuring the unknown angles. Now you can see that the component is bigger than the sine bar. So the setup will be like this. So the component will be placed over the surface plate, and on the tapered surface we are actually placing the sine bar like this. Okay, in the reverse order. So it has to be rested with its top surface. Then in this case, we have to use an additional equipment, that is the vernier height gauge. So we have to fix the vernier, we have to fix a lever type dial indicator on the vernier height gauge. Then that is actually used as a fiducial indicator, because that indication is actually used only for calibration purpose. We are not actually taking the reading for our final computations. That's why it is known as fiducial indicator. So initially what we are doing, we are actually placing that in this side, that is the left side of the workpiece. Then by moving this portion downwards, we will just touching this stylus of the dial test indicator to the ball, top surface of the ball on one side. Then we are giving some small pressure, so such that we will have some prefixed deflection. Say that deflection will be 20 divisions. Okay, some 20 division deflection should be given on the dial of this dial test indicator, so that will be fixed. Then we will remove this one from this position, and it will be moved to the right hand side. Then here again we are actually moving down the sliding unit of the vernier height gauge, and it is again just touching the surface of the ball on the right side. Then again we are actually giving a slight movement in the downward direction and making the same 20 division deflection on the dial. So now we can tell that we are exerting the same pressure on the both sides. That is why it is known as fiducial indicator. Okay, so after taking these same deflections, we are actually taking the reading of the vernier height gauge. In the first case, it is H1, and in the second case, it is H2. So our H is equal to H1 minus H2. Now the angle is sine theta is equal to H1 minus H2 divided by L. So we can find the theta from this equation. In the limitations of sine bar, the accuracy of the sine bar depends on the center distance, accuracy of the center distance between the two precision rollers. Okay, so that is the one point, and another one is that it is reliable at angles less than 15 degree. So more than 15 degree, this one is not at all giving reliable readings, because settings is also very difficult. And why it is not accurate, the reasons are pointed over here. So first is physically clumsy to hold in position, then body of the center obstruct the gauge block stack when it is relieved. So gauge box stack cannot be placed below the sine bar above this 45 degree. Then slight errors of the sine bar cause large angular errors. Long gauge stacks are not nearly as accurate as shorter gauge blocks. That means the gauge block number of pieces should be minimum, so that cannot be maintained if angle is more. Then difference in deformation occurs at a point of roller contact supporting the surface and the gauge block, because at a higher angles the load is shifted more towards the fulcrum roller. So these are the reasons why it is not using more than 45 degree. A modification of a sine bar can be seen in another equipment known as sine center. So this is actually a modification of sine bar in which we are actually additionally providing two centers. Okay, so these centers are actually provided for holding cylindrical workpieces. So normally a sine bar can hold rectangular workpieces only. So cylindrical workpiece is using, we can have to use sine center, and the other working principle, everything is same. Thank you for watching.